showing you some results from our new GDIGS survey, which is a large survey of the diffuse ionized gas in the Milky Way. I'll talk a little bit about my dissertation research, which was mostly on the influence that high mass star forming regions have on the diffuse ionized gas. And in the end, I'm going to show you some very recent observations that we did with the GBT that reveal a quite interesting and strange signature in the diffuse ionized gas. So the main idea is that when you have massive stars, they affect the interstellar medium of our galaxy. And they do that because they emit a large amount of ionizing radiation. Most of that ionizing radiation will be absorbed by their surrounding H2 region, but some of the ionizing radiation can escape through the H2 region boundaries and into the diffuse ISM. And there, the radiation will ionize part of the ISM, and it will create a phase known as the diffuse ionized gas, or DIG. And we don't really understand the DIG very much, especially in our galaxy and in the midplane. It is very difficult to observe this diffuse ionized gas because there is a lot of extinction. And there has been very little research done in our galaxy on the connection between this diffuse ionized gas, which presumably maintains its ionization from high mass stars and H2 regions, and the connection of this gas with H2 regions themselves. So I've structured the talk in that I will first talk a little bit about H2 regions and the diffuse ionized gas and what they are and how they interact. The second part of my talk is titled Ionization Profiles of Galactic H2 Regions, but this will mostly focus on the connection between H2 regions and the diffuse gas. I will then talk about the GBT Diffuse Ionized Gas Survey, or GDIGS, which is now completed, and I've got some really nice images to show you there. And in the end, I'll show you some of the new deep pointed observations that we did with the GBT. So I'm sure many of you have seen this idealized picture of what an H2 region is. You have a high mass star in here in the middle, which originally exists in the uniform medium of pure hydrogen. This star emits a lot of ionizing photons isotropically, which create this spherical region of ionized gas known as an H2 region. Between the fully ionized H2 region and the surrounding interstellar medium, so the surrounding neutral and molecular hydrogen, there is a region called the photodissociation region, or PDR. That's a region that's mostly neutral, but the chemistry in the PDR is still strongly affected by the radiation from the star. The problem is this is an idealized picture, and in reality, H2 regions are pretty messy. If you just look at the middle image here, what you have here is a infrared composite image. The red color in here shows emission from hot small dust grains. The red emission basically traces the ionized volume of an H2 region. By the way, this is the H2 region M20. And the green emission you see here is from polycyclic aromatic hydrocarbons, which are excited in the PDR around H2 regions. So the green emission here is basically the boundary between the H2 region and the surrounding ISM. And you see it looks nothing like this beautiful, nice symmetric layer that we saw in the previous image. It has some structure itself, overdensities, underdensities, holes. So it's really no surprise that a lot of the photons that are generated in here would probably be able to escape through the PDR somehow. And the idea is that these escaping ionizing photons leave the H2 regions and travel into the interstellar medium, where they ionize part of the interstellar medium. And that ionized part of the ISM we know is the diffuse ionized gas, or DIG. It's a pretty major component of the interstellar medium. It accounts for about 20% of the mass of the interstellar medium. But we don't know much of it because there haven't really been many galactic observations that trace the diffuse ionized gas, because, as I said, it is difficult to trace. And I'll get back to that in a minute. What we do know is that its typical temperature is roughly that of H2 regions, about 10,000 Kelvin. The scale height varies depending on how you define things, but it's usually somewhere in the order of 1 kiloparsec, and its density also varies by quite a bit. The idea is that if photons that escape from H2 regions maintain the ionization of the DIG, then the emission from the diffuse gas should roughly follow that of H2 regions. So it should be stronger near H2 regions than somewhere else. But again, we don't fully know the details. And especially, we also don't know the details of the relationship of this photon escape and the H2 region sizes or luminosities. So we don't even know how many photons can escape from H2 regions. There have been quite a few studies done on the diffuse gas in nearby galaxies, many of those in optical lines, such as H alpha. This is an image of the nearby galaxy NGC 157. This was published almost 20 years ago by Almudena Zurita. And what you see here in the color scale is H alpha emission, which traces ionized gas. And all these black dots that are removed from this image are discrete H2 regions. So the idea is that all that's left here in the color scale is diffuse ionized gas that's not associated to discrete H2 regions. So this is great when looking at external galaxies. There are some problems with that. And I'd say the main problem here is that the resolution is quite limited. So you won't be able, from an H alpha image like this, to separate emission from small H2 regions from emission from the diffuse ionized gas. And another issue that's less important in studies of external galaxies, but more important in our own galaxy, is that there's always some dust along the line of sight, which might attenuate the visible light. So when it comes to our own galaxy, our solution to that problem is we will use radio wavelengths. We'll use the GBT. These are essentially unaffected by extinction. And the resolution is still good enough that we can separate most H2 regions and the diffuse gas. So that's what we started doing a few years ago. And the main science question we wanted to answer here is, what is the connection between star formation regions and the diffuse ionized gas? And the way we looked at that was we used GBT observations of radio continuum and radio recombination lines. Radio recombination lines are a great tool to trace ionized gas. They very nicely trace the thermal ionized gas. They are not affected by extinction, really. The only issue is that they're faint. But, and I will get back to that in a minute or so, with the new Vegas receiver, we can observe a large number of radio recombination lines at the same time. And after averaging them together, we really increase our sensitivity. And that really made it possible that we can detect these radio recombination lines from the faint diffuse ionized gas. So this work has been published in 2 papers. The first was a case study of a single H2 region where we tried to trace how radiation escapes from the region, which we then followed up with a larger study of 8 separate galactic H2 regions. Initially, we looked at the H2 region NGC 7538. It's in the outer galaxy, which was great for our purpose because there's not a lot of confusion along the line of sight. So we can say that any diffuse ionized gas we might trace around the H2 region is probably in some way related to the H2 region itself. What you see here on the left-hand side is a radio continuum image of NGC 7538. And you can already see that the region is here in the center, but there's quite a bit of radio continuum emission outside of the region. In particular, the photodissociation region, the PDR surrounding the H2 region, that's indicated over here on the right-hand side. It's kind of between the solid white line and the dashed white line right here. So in particular, there's a lot of radio continuum emission outside of that PDR. And that suggests that quite a few photons from the H2 region must be able to travel through the PDR somehow and escape into the interstellar medium surrounding the H2 region. Here we found that about 15% of the radio continuum emission is outside of the PDR. So this was a very nice tracer that showed us that we do have a significant amount of radiation leaking into the ISM. The other thing we did here is we did a bunch of discrete pointings where we observed radio recombination line emission, both within the H2 region and outside of the H2 region. And our main finding here was that when you plot the radio recombination line intensity versus the distance from the H2 region, the intensity decreases as you go further out, which is what you would expect if photons leak from the H2 region and ionize the diffuse gas. But also that we can approximate this decrease quite nicely with a power law function. We did a similar analysis near the giant H2 region complex W43. So W43 is shown down here, and GC7538 is shown up here. And we find essentially the same form of decrease. We also find a power law decrease around W43, but the slope of that power law is much shallower. So the idea is that giant H2 regions will affect the interstellar medium on much larger scales than small H2 regions. This isn't really a big surprise. It's what you would probably expect, but the fact that we were able to quantify this with a power law was quite interesting. And that really led us to follow this up on a bunch more H2 regions. These are 8 more H2 regions that we have in the galactic plane, where we essentially did the same study where we observed radio recombination lines from discrete pointings, both within and outside of these regions. And we find essentially the same thing. This plot is a little more complicated. Here on the y-axis, you have the radio recombination line intensity again. What you have on the x-axis is the distance from the H2 region, but it is normalized by the region size. So if you're at a normalized distance of 1, then that means you're at a distance of 1 PDR radius away from the center of the region. At a distance of 2, you'd be 2 radii away, and so on. And what you see here is that with the exception of essentially just 2 regions, the exceptions are just Orion and M17, all the H2 regions have roughly the same slope when looking at the decrease in radio recombination line emission. So that not only suggests that larger regions affect the ISM on greater spatial scales, but there's a very strong correlation between the size of the H2 region and how far out the H2 region will affect the diffuse ionized gas emission. So those were still just 8 H2 regions. So our next project was to expand this to include a lot of H2 regions in the galaxy, to include thousands of H2 regions. And this can only be done with a fully sampled survey. And this is kind of what led to starting the GBT diffuse ionized gas survey, or GDIGS. GDIGS is a large-scale survey of the diffuse ionized gas toward the inner galaxy. It covers about 50 square degrees or so. It's a very high sensitivity survey because we got the whole collecting area of the GBT. And it has a relatively high spatial resolution and a very high spectral resolution as well. So we're not only able to detect radio recombination line emission mostly everywhere in the inner galaxy, but we also know its velocity, and therefore it can trace the kinematics. GDIGS was awarded over 400 hours of telescope time. This was split up in a few separate projects, with one main project and a few projects to map larger areas. And we're really happy the project is now complete. Our data reduction is now complete, and we will release the radio recombination line data to the community very shortly. So this is what our observing setup consisted of for GDIGS. We used the C-band receiver, spanning the whole range from 4 to 7.6, 7.7 gigahertz. And we use that in combination with the Vegas backend in a mode called mode 21. This mode uses all 8 banks, so we get a total of 64 IFs, of 64 individual frequency windows. Each of these frequency windows is 23 megahertz wide and has 8,000 channels. And at those frequency, that corresponds to a spectral resolution of about 0.2 kilometers a second. So with these 64 IFs, we can observe a lot of individual lines at the same time. 22 of these IFs were taken by hydrogen alpha recombination lines. Alpha recombination lines are recombination lines where the electron will jump down one principal energy state. These lines stretch from about 95 alpha to 117 alpha, with the exception of 113 alpha, which is compromised by nearby beta lines. We have 26 hydrogen beta recombination lines, so these skip 2 electron levels. And we have 8 gamma recombination lines, so these are a difference of 3 electron levels. Beta and gamma recombination lines are quite a bit weaker than alpha recombination lines, so they don't tell us much more about the distribution of the diffuse gas, but we can use those to see whether the diffuse gas is in local thermodynamic equilibrium, so they're still useful to us. And simultaneously, we observe 8 molecular lines. Due to the fact that it's a fully sampled survey and our integration time per beam is not that high, we really only have good detections for 2 molecular lines, which are formaldehyde and methanol. There are a few constraints on the observational side. The baselines are not great near the receiver limits, so we try to really stretch out our bandwidth here. But near the receiver limits, the baselines are not great. So overall, we have about 15 good H and alpha lines. And these 15 lines are also not really strongly affected by RFI, which is great. What we then do is we average all these 15 lines together to make one oversampled HN alpha radio recombination line data cube. So we can average these all together to increase our sensitivity. The mean frequency of that average cube is about 5.8 gigahertz, and the spatial resolution is 2.2 arc minutes. This spatial resolution is enough to disentangle most small H2 regions from the diffuse ionized gas. And our spectral resolution of our final data is 0.5 kilometer per second. So we really also get all the velocity information of the gas. For this survey, at the highest frequency, our integration time per beam is 18 seconds. So for our average beam at a 2.2 arc minute resolution, this integration time per beam is a little higher. It's about 30 seconds. All right, and these are our first results from GDIGS. Over here on the top, in the background, you see a Spitzer infrared image, and overlaid with this yellow line, you see the overall coverage that we have with GDIGS. This is in galactic coordinates. So over here, we have a galactic longitude of 0. This is the galactic center. We started the GDIGS survey at a longitude of -5 degrees or 355 degrees over here. This is around the longitude limit that the GBT can map efficiently. And we go all the way up to about 32 degrees in longitude. In latitude, our nominal range is 0.5 degree off the plane, but there are a couple of regions where we observe further off the plane. And these are usually regions where we have more star formation, so we also expect more diffuse ionized gas emission further away from the plane. So one of these regions will be the galactic center here, where we go up to about 1.3 degrees. We have another region over here at 24 degrees longitude. There's a lot of star formation in here that you can somewhat make out in the infrared image. So we go a little bit further up here as well. And over here, we have the giant H2 region complex W43. So we go further out here as well. We also have some smaller explorations at larger longitudes, for example, at 37 and 43 degrees, which are nominally part of GDIGS as well. Overall, our data quality is quite nice. Here in the next panel, you see an image of the noise level, which is relatively uniform. It is a little bit higher here on the lower longitude end than on the higher longitude end, but that is mostly because at lower longitudes, we are observing on average at lower elevations. And over here in the third panel, this is the moment zero radio recombination line map. So what you see here is the integrated intensity of the hydrogen radio recombination lines averaged together. So these trace ionized gas from discrete H2 regions, but also from the diffuse ionized gas. I know this is a little small here. I will zoom into one of these regions later on. The main take-home message here is just we really detect radio recombination line emission essentially everywhere along the survey range. Granted, a lot of this radio recombination line emission comes from discrete H2 regions. In the bottom panel here, you see all these little circles. Each little circle here is a known H2 region. So a lot of the emission comes from the H2 regions, but there's also quite a bit of space in between the H2 regions left in here, where we have emission that is clearly from the diffuse ionized gas. This is just another image I really like to see the data. These are also integrated intensity maps of our GDIGS radio recombination line data, but at different velocities. So that top panel here is everything integrated from 0 to 20 kilometers per second. The next panel is 20 to 40 kilometers per second, and so on. And this really nicely shows you the rotation of the galaxy, because here at lower velocities, you have more emission at lower longitudes. And as you go up in velocity, you see more and more emission at larger longitudes. One exception being, of course, the galactic center, where you have a lot of emission at all velocities due to the very complex motions around there. And here we have a longitude velocity diagram of our whole GDIGS survey range. So on the y-axis, you have the galactic longitude in degrees, starting from 355 or -5 down here to our overall range to 32 degrees. And on the x-axis, you have the velocity. The background in this image here is the radio recombination line data from GDIGS. So you see very strong emission over here near the galactic center at 0 degrees longitude, which stretches over the pretty much entire velocity range. But you can really nicely trace the rotation of the galaxy and even somehow the individual spiral arms here as you go up in longitude. The blue crosses you see here are all known discrete H2 regions. So overall, the radio recombination line emission very nicely follows that of H2 regions, which is what we would expect if the diffuse ionized gas maintains its ionization from photons leaking from H2 regions into the interstellar medium. There are some regions where this correlation is stronger than others. For example, we have quite a bit of diffuse gas emission down here, where we don't really have many H2 regions. Over here, maybe a little bit over here. But in general, they're very nicely correlated. You might also note this band up here. That's not real emission. That is RFI from 2 individual frequency channels that made it into the average data. Adapted our pipeline a bit. So with our most recent data products, this RFI is all gone. One thing we did on this data is we applied a spectral decomposition pipeline. So what that means is we extracted from each pixel that we had in our maps a spectrum and then automatically fitted Gaussians to that spectrum to find the exact centroid velocities of the diffuse ionized gas emission. And what is shown over here in the right-hand side are in the grayscale, those are the results from our spectral decomposition pipeline. So essentially what that pipeline does is it fits lines at each pixel, and then from these fits, you can extract the central velocity and the width of the line. And this is just exactly what is plotted here. And the really nice thing about this is that it essentially removes all the noise in the data, and you're only left with the clear signals that you detect from the data. And overall, the correlation to the actual data is very strong, as we would expect. But it does filter out some of the very diffuse emission right in here, for example, that we can see a bit more strongly in the real data. All right, so zoomed into these maps, our emission looks typically somewhat like this. What we have here is the large H2 region complex W43 here in the center and G29 over here. And these are some preliminary GDIGS data that we started analyzing about a year and a half ago, and which were published earlier this year. So these are H2 regions that are very luminous. So our hypothesis here was that these H2 regions should ionize a lot of the interstellar medium surrounding them, because presumably they leak a lot of ionizing photons into the interstellar medium. And from a first glance, it looks like that's what we observe. We detect radio recombination emission essentially everywhere within 1 degree or so of the galactic plane. One downside of plotting it like this, though, is we can't really disentangle nicely what of this emission comes from discrete H2 regions and what's really due to the diffuse ionized gas. So what we did is we filtered out all the emission that we think comes from discrete H2 regions. And we do that by using the WISE catalog of galactic H2 regions. This is an H2 region catalog that was compiled by Lauren Anderson et al. A few years ago. And this catalog gives us the location, sizes, and velocities of all known H2 regions. And it also gives us all H2 region candidates, which show the characteristic H2 region morphology in the infrared, but for which we don't really have any velocities. So all these circles you see here are either known H2 regions or H2 region candidates. And this is a great tool because we can now remove all the emission associated with these H2 regions, and we're left with only the diffuse ionized gas emission around them. Going forward, what we did is we tried to find a model that would explain the diffuse ionized gas emission based only on the locations, sizes, and intensities of the H2 regions. So for this model that we created, so this was purely empirical, our inputs were really only the locations of the H2 regions, the sizes of the H2 regions, and the intensities. And we assumed for this model what we found earlier is in that the diffuse ionized gas should roughly follow this power law fall off as you go further away from H2 regions. So when plugging that in, we found that the model reproduces the actual emission very nicely. So over here on the left-hand side, you have the model emission. And over here on the right-hand side, you have the difference between the model and the data. And we also found that in order to make the best fit model, the escape fraction, so the number of photons escaping from a region over the overall number of photons generated by the ionizing star, should be roughly the radio recombination line intensity of the region to the power of 0.14. So this just tells us that in order to make our best fit model, we need to allow more luminous regions to leak a larger fraction of radiation into the interstellar medium. This is something that's been suggested by extragalactic studies and theoretical studies already, but it was very nice to see that that is also the case when looking at these smaller and more nearby H2 regions in our own galaxy, that this really holds up when also looking at very compact H2 regions and not just the giant H2 regions we can observe in nearby galaxies. In numbers, this would imply that assuming a typical compact H2 region has an escape fraction of about 20%, these large H2 regions would need escape fractions of about 30%. So those are our first results from GDIGS. And now very briefly, I want to talk a little bit about some deep pointed GBT observations we did of the diffuse ionized gas in the midplane. So what we did is so far, we only really looked at the diffuse ionized gas near H2 regions. the diffuse ionized gas, where we could really say, okay, this is due to escaping photons from these particular H2 regions. Here we made pointed observations still in the galactic plane, but as far away from H2 regions as we could. And we found one of these positions at a longitude of 20 degrees and another at 45 degrees. So here we really trace the diffuse ionized gas that should not really be associated with any particular H2 region, but rather a diffuse background. Over here on the right-hand side, you see a result for G45, the region at 45 degrees. What you see here in green is the spectrum that we observed for this particular position. And we overplotted that onto a longitude velocity diagram. So in the background here, you see this gray emission, which is 13CO emission from 44 degrees to 46 degrees in longitude. And the red circles and black circles are the locations and velocities of discrete H2 regions with radio recombination line emission or discrete molecular clouds. So this position that we observed here, G45, shows us a very nice spectrum. That peak here is around 3 millikelvin, so it is very faint emission. But overall, it's pretty much what we expected. The velocity of that spectrum matches the velocity of nearby H2 regions quite nicely. So even though we chose a position that's a little further away from H2 regions, it seems that this diffuse ionized gas is still somewhat associated to these H2 regions. It still looks like it is ionized by photons escaping from these H2 regions at this velocity. For our other position, our result was a little bit more surprising. So this is our position at 20 degrees, and you see we have two components here in the spectrum, one at 50 kilometers and one at about 110 kilometers. The 50-kilometer component can be explained nicely by nearby H2 regions, but the component at 110 kilometers, there are really no H2 regions at that velocity. So where does that peak come from? Well, the answer is we don't know. We followed up on this a little bit by looking at previous observations of nearby H2 regions to see if we found any detections at 110 kilometers per second. This is what's shown here. In the background, you have our GDIGS data at 110 kilometers. And all these individual dots are discrete H2 regions. The dots in blue are H2 regions where we detect something at 110 kilometers. It may not be a real signal at exactly that velocity, but there's some emission at 110, whereas the red points have no emission at all at 110 kilometers. So this suggests that the signal is quite extended. It extends from 20 degrees down to almost 19 degrees in longitude. So this suggests that the signal is probably really from the diffuse ionized gas. But we don't know what its ionization source is. We don't really see any discrete H2 regions that are centered at that velocity. Maybe it's H2 regions without that characteristic infrared morphology. Maybe it's runaway stars. And another problem is we don't know why that line is so strong. It's almost 10 millikelvin strong. So this implies that either the path length of the ionized gas is quite large or the densities are large. So one hypothesis could be that maybe we're looking at like an illuminated dense surface of a larger molecular cloud. There is some molecular gas at that velocity. But again, it would have to be a very large cloud. It's quite extended in longitude. And again, we still come back to the problem to what's the source of these ionizing photons. So to me, this just says that it looks like there's still much about the diffuse gas that we don't understand. And for this problem in particular, we have put in a follow-up proposal to observe more positions near G20, do very deep pointed observations there, so we can better constrain the extent and the strength of the signal, which will hopefully give us some clue as to its origin. So stay tuned for that. I'm going to leave my conclusion slide up here, and I'd be happy to take any questions. Thank you.
Thanks, Matteo. So I guess I have a question. So how do the kinematics of the dig compare to the nearby H2 regions? Like, are you seeing broader line widths compared to what you detect in like the H2 regions, or do you see any type of velocity gradients between the dig and the nearby H2 regions? So how do the kinematics compare between the two?
That's a very good question. So overall, the velocities are usually very similar. So if we have an H2 region at a given velocity, we can assume the dig has a similar velocity. That's strictly only true if we're close to the H2 region. If we go a little bit further away, and I'd like to go back to this image here. So here we observe the dig position that is pretty far away from any H2 regions. And here we see a very broad line in the dig. So that line has a width of, so I'm talking about the 50 kilometer per second line here. That has a width of about 60 kilometers or so total. And I think what we observe here is simply all the dig emission at maybe different distances ionized by different H2 regions, which added together gives us this broad line. So I would say in general, they're very tightly correlated, but because with the dig, we usually observe a larger path length and we observe more emission close to several H2 regions at different velocities, often we observe very broad lines. As to this line, this is quite narrow. This is more like an H2 region line. So yeah, still a mystery.
Okay, thank you. Any other questions for Matteo?
Also, I just wanted to say, if any of you have any ideas as to what this could be, please let us know. We're pretty stumped by this result.
I guess I had one other clarification question. So on slide, I think it was 21, you show the list of like molecular lines that you include in your data set. And I saw that you had HCN in there. And I thought HCN was closer to like the 3 millimeter range. Is there like a different transition that's down at C-band?
Yes. I'm not exactly sure about the frequency of that transition.
Okay.
But I don't think we had a detection anywhere. So we haven't gone over all these molecular lines in a lot of detail because our primary data product is really the alpha recombination lines. And adding most of these was sort of an afterthought to really utilize all the IFs that we were given. But from looking at the data, we only have clear detections in formaldehyde and methanol.
Okay.
So I don't think we see anything here.
All right. Any other final questions for Matteo?
Matteo, for that position that was away from any H2 regions, did you look at the formaldehyde and methanol for that, or just the recombination line?
That's a good question. I have not looked at the formaldehyde and methanol. That's a good idea. I'll have a look. One of the issues we had at this position is that this is still slightly under the threshold of GDIGS. So this is only the pointed spectrum you see here. When you look at the GDIGS map, you don't really see any of this emission because they're still not intense enough. But yeah, that's a good idea. I'm going to look at the formaldehyde and methanol data to see if there's anything there.
Just looking at the CO sort of filamenty structure there, I would guess that you would see something, but
yeah, the CO is also a little puzzling because we do have some CO down here at like that extends up to almost 20 degrees, but at 20 degrees we we don't really detect any CO at that position, so and that velocity. So there is some CO nearby, but yeah, my guess is it's probably somehow related to this, but it's still a lot weaker than the CO we see here at 50 kilometers, but yet our radio recombination line is so strong. Thanks, Will.
Yep.
All right, so I think we will conclude here. We will not have a science lunch next week since we are doing the GBO and Arecibo Observer Training School. So our next talk will be the following week. And our speaker then is going to be Jesse, who is our new postdoc here at Green Bank. So we'll see you all then.
Thank you.